Hi, thank you so much for joining me. I want to talk about the application of Coulomb's law to atomic structure. I think, especially as you build into comparing one element to another element, one atomic structure to another atomic structure, Coulomb's law has very powerful explanatory powers. Now, we're going to be looking at it from a very qualitative sense. And so from that perspective, what we want to look at is that as you increase charges, in this case, we have the charge on a nucleus. So that's the nuclear charge compared to the charge on an electron. So we have a positive and a negative. As you increase charge, and since this is positive and this is negative, as you increase charge, you're going to make the potential energy increasingly more negative. Okay, so if we were to have a positive and a negative for our potential energy, and this is distance, we would talk about being more negative for greater nuclear charge and less negative. So this would be a Q of, I'm just going to, look at, +9 for fluorine compared to a Q of, say, +3 for lithium. Okay, so the fluorine one is going to be more negative than is the lithium one. Okay, and that's a good thing. Negative potential energy means more traction in chemistry. Now, let's look at this in terms of the distance. All right, as you increase the distance, all right, you decrease the magnitude or make it less negative. Okay, so as you increase the distance, we're talking about a higher or more or less, less negative potential energy. So let's graph that. If we had, as we talk about an electron coming into proximity of a nucleus, so as they get closer and closer together here, closer and closer together, they start to sense the attraction. Attractive forces are negative. That's going to reach an optimal, and then they get too close and it starts to become repulsion. Okay, so as you're comparing elements, to summarize, increased nuclear charge, all right, you have a lower or more negative potential energy. As you increase distance, you have a higher, inversely proportional, or less negative. I try not to say big or smaller because that negative in there can make that a challenging concept to understand. Well, what does that mean? Let's compare two elements. And again, this is all very, very qualitative. So if this is the nucleus, if I have Z is equal to, again, let's do +9 compared to Z equal to +3. If you're talking about the N equals 1 electrons, that electron is closer in fluorine than that electron is in lithium. So not all N equals 1 are the same energy level. All right, and you will be able to apply this to periodic trends as you look across a period. You'll find that atomic radius decreases. That's because the N equals 1 is closer to the nucleus as you increase nuclear charge. Now, as you talk about different energy levels, so if we had N equals 1 and then we had an energy level for N equals 2, N equals 1, N equals 2, N equals 3, okay, and so forth, they converge and get closer and closer together, right? As you increase in energy level, so as you increase that energy level N, right, you're further from the nucleus. You're at a higher or less negative potential energy. So if we could go back to that picture and kind of superimpose on that image, we could envision it, the nucleus down here, N equals 1, N equals 2, N equals 3, N equals 4, and so forth, until the electron is ionized or gone. Okay, as it got further and further and further from the nucleus. Okay, my pictures aren't ideal, but I hope they give you some sort of an image of what we're talking about and how we will be applying Coulomb's law. But I want you to be really, really careful here, and I saw this on the reading, is you want to watch that distance. You've got to define the distance. In this case, our distance is between the nucleus with its nuclear charge, which at a first introductory level you can think of as the number of protons. Gets a little complicated, but that's a story for another video. But you're looking at the distance between the nucleus and a particular electron. Okay, so make sure if you're going to apply Coulomb's law that you define that term. So, okay, thanks for joining me. I hope this gives you a little insight into potential energy attractive forces and how that's going to be applied to the structure of an atom. Thanks for joining me.